presented by the Dr. Marina Caballero Diaz. The paper presents the results of the hydrogen production from catalytic decomposition of methane using ruthenium catalysts supporting gamma alumina. The gamma alumina supports were synthesized from the three different precursors, and then the synthesis of the catalyst at 1% of ruthenium was performed. The reaction was carried out from 400 to 750 Celsius degrees. The capital P catalyst obtained the best production of hydrogen, 22,000 parts per million, and the highest methane conversion, 58% at 700 degrees, besides presenting the greatest stability at his temperature. The MERC and the Sec2 oxide of aluminum catalyst has lower catalytic activity. Also, they were observed on the stream output uncapped methane and small amounts of ethane and methane, less 1%. The type of carbon produced in the three catalysts was graphite type and was deposited in mainly on spore. In the last stage of this work, the reaction mechanism was analyzed, applying the hypothesis of the approach to a steady state of the intermediaries, where the composition of methane in the gas phase involved in the formation of free radicals. With increasing world population, industrialization, and urbanization, the demand for energy is rapidly increasing. Currently, around 85% of the total energy in the world is obtained from non-renewable resources such as coal, gas, or oil. This situation contributes to climatic change. It has been estimated that in the coming decades, world oil reserves will decrease in an accelerated manner due to the fact of the number of existing oil fields with respect to the world oil demand is decreasing. Therefore, this will be a strong impact on the economy of countries that have not developed alternative technologies. Consequently, progressive governments of various countries have proposed a radical change from oil economy to one of hydrogen. It is possible that one day hydrogen may replace fossil fuels in various applications such as automobiles and power plants. At present, hydrogen finds application as a chemical compound instead of a fuel in commercial operations. But if hydrogen is used to replace existing fuels, suitable methods of its large-scale production must be developed. The precursor salts that has been used for the obtention of gamma alumina was capital B boehmite and Sec2 butoxide of alumina. Once obtained, those supports was deposited 1% by weight of ruthenium by human impregnation. Subsequently, we impregnated different supports. The solid was stirred by 3 hours and finally reduced on hydrogen flowing at 500 degrees by 5 hours. The different catalysts were tagged by different ways, where Ru was ruthenium, B capital B boehmite, and S Sec2 and M merc. In the texture analysis to the calcium catalyst at 650 Celsius degrees, entire isotopes of adsorption presents were classified according to the UPAC as type 4, which is characteristic of mesoporous materials. The catalysts present hysteresis type H1, having the same type of pore, which usually observed on mesoporous materials with a very narrow pore size distribution and conglomerates of spheroidal particles of uniform size. The BET specific surface areas of the fresh catalysts are reported in Table 1. The surface areas obtained from the different precursors present variable areas. The pore size distribution in Sec2 was narrow, from 30 to 120 Armstrongs, while for the MERC and capital B catalyst, the pore size distribution was wider, from 30 to 160 Armstrongs and 30 to 190 Armstrongs respectively. The catalyst showed the characteristics of gamma alumina phases. No signals corresponding to Ru crystals were detected in any catalyst studied, which indicated that metal particles were small and probably due to the low concentration, which could not be detected by the equipment. The diffraction pattern of the catalyst showed differences in the crystallite size of gamma alumina. The production of hydrogen was carried out through the catalytic composition of methane by 1% by wet ruthenium catalyst support on gamma alumina from different precursors, capital B, aluminium, sec butoxide, and merc. The reaction was carried at 400, 500, 600, 700, and 750 Celsius degrees with a previous activation with nitrogen 30 milliliters per minute and injection of 2 milliliters per minute of methane as reagent. Figure 4 shows the profiles of methane conversion as function of temperature. It can be seen that the conversion of methane increased as the temperature increased from 400 Celsius degrees to a maximum conversion to 700 degrees, followed by decreasing conversion in all three catalysts at 750 Celsius degrees. The present work describes the effect of precursor salt of gamma alumina for the production of hydrogen in the methane decomposition in the range of temperature of 400 to 750 Celsius degrees. The supported catalysts were prepared by the impregnation of ruthenium as precursor. High acidity, volume, great pole diameter, and high specific area of sectbutoxide and merc catalyst favored the high catalytic activity. Sectuboxide catalyst has the highest methane conversion and hydrogen production at 700 Celsius degrees, while sectuboxide catalyst obtained the lower production of hydrogen. The catalytic stability reaction was carried out and maintained for 10 hours at 700 degrees for the three catalysts, which showed that sectuboxide catalyst was completely desactivated, and the type of carbon produced during the reaction was graphic carbon, which was deposited in the middle of the spot.